Humanity is at the outset of the solar age, where sunlight will be used not only to provide renewable electricity, but also to drive chemical synthesis of fuels and materials to power and build for the next millennium. The storage of sunlight in liquid fuels via artificial photosynthesis is the focus of fundamental research being done at the Lawrence Berkeley National Laboratory and inside Building 30, home to the former Joint Center for Artificial Photosynthesis, JCAP, and now the Liquid Sunlight Alliance, LiSA. My name is Jason Cooper, and I'll be your host and tour guide. Thanks for joining today to learn together about our research and vision for the future, which seeks to change how we harvest and store solar energy to provide green, renewable fuels. Located in the hills overlooking Berkeley, LiSA at LBL, founded in 2020 with Lead Institute Caltech and partners at LBL, NREL, SLAC, UC Irvine, UC San Diego, and University of Oregon, this Department of Energy-funded research consortium is inspired by photosynthesis in plants, where scientists are designing materials and chemical processes to convert sunlight into chemical energy using only components of air, water, carbon dioxide, and nitrogen. Directly producing liquid fuels from this abundant feedstock would provide an efficient way to store and dispatch solar energy on the pathway toward energy independence. Before we begin the tour, let's start with an explanation of how the hydrogen evolving device shown at the beginning actually works. The black square in the middle is a photovoltaic chip consisting of a multi-layer semiconductor device. Surrounding it is a thin transparent membrane which allows for ions like protons to be transported through it while blocking products like hydrogen, oxygen, and ethylene from crossing over. The shiny metal layer deposited on the membrane is a catalyst, which improves the efficiency and selectivity of a desired chemical reaction. When the semiconductor is exposed to sunlight, it generates high-energy electrons in holes. The holes are swept to the back of the device, while the electrons move out of the semiconductor and into the surrounding catalyst layer. When protons and carbon dioxide come in contact with this negatively charged catalyst, they are reduced. They gain electrons into chemical products such as ethanol, carbon monoxide, hydrogen, and ethylene. These products are blocked by the membrane so they can be collected, separated, and stored. The positively charged oxidizing species, the holes, show up on the back of the device, where they are transferred to a catalyst specifically well suited for oxidizing water, which forms molecular oxygen. This gas phase species also bubbles out of the cell. The co-production of hydrogen and oxygen in the same cell therefore necessitates the membrane, allowing for the safe production of separated hydrogen and oxygen streams, as the mixture of the two can be highly flammable. Let's now head down into the labs and see how these materials are scaled up, evaluated, and tested. The deposition lab houses equipment for e-beam evaporation and sputtering, which allows for single or multi-element metals, oxides, and nitrides to be deposited on a variety of substrates with precise control over composition and thickness, ranging typically from 1 to 1,000 nanometers. As substrates such as quartz, silicon, conductive FTO-coated glass, plastics, and silicon nitride windows can be utilized, the same materials can therefore be studied by a variety of different advanced characterization methods, including optical and X-ray spectroscopy, electron microscopy, and photoelectrochemical testing. Here we are looking at a sputtering process in which copper and bismuth targets are being sputtered in a mixture of argon and oxygen to create a copper-bismuth oxide thin film on the spinning quartz substrate mounted above. This material is being investigated as a photocathode, which drives the types of reduction chemistries referred to earlier. And here's the result, a uniform coating of the copper-bismuth oxide ready to be studied. Thousands of new material compositions and catalysts can be rapidly screened using high-throughput synthesis and experimentation methods being developed at Caltech. Each inkjet printed dot represents a unique 4-element mixture which can be tested for its optical and photoelectrochemical performance to discover new semiconductors and catalysts with unique or tailored properties. These libraries can be deposited on known semiconductor substrates as well, to identify catalysts which couple well electronically with the underlying semiconductor. Once an optimum material is identified, it can be scaled up using sputtering and further evaluated and tested using various laboratory experiments. Let's go take a look at some of the experimental techniques we employ to understand material properties. X-ray photoelectron spectroscopy, XPS, uses high-energy X-ray light to photoexcite core electrons, such as those in the oxygen 1s, out of the material and into the ultra-high vacuum chamber where the kinetic energy can be measured by the hemispherical analyzer. As such, the binding energy of the core electrons can be determined. The binding energy of the core electrons are distinctly different across elements of the periodic table, allowing for the assignment of elemental makeup of unknown materials. The binding energy for a given element is sensitive to the oxidation state and the chemical environment, therefore allowing for the determination of the relative composition of component elements such as the copper to bismuth ratio in our sputtered thin film. Furthermore, the very topmost elements can be identified using helium-ion scattering spectroscopy, which is important for helping understand the function of multi-element catalysts as the surface atoms are the ones engaging in the catalysis. XPS measurements are critical to inform the composition and electronic structure of materials. X-ray diffraction allows us to evaluate the crystalline nature of the materials to verify we have grown the correct phase, the phase purity, temperature-dependent properties up to 1000 Celsius, determine the orientation of the crystallites on the substrate, verify heteroepitaxial growth, and measure the thickness with nanometer precision. The wavelength-dependent optical properties can be determined by variable angle spectroscopic ellipsometry, which informs how materials absorb, reflect, and transmit sunlight, as well as provides a sensitive method for determining the sample thickness with nanometer precision. Moving into the laser lab, this space houses several techniques which employ high-powered continuous and pulsed laser sources to investigate many types of light-initiated processes. One such technique, shown here, is transient absorption spectroscopy, which uses a pulsed laser with pulse duration of 100 femtoseconds. That's 1/100th of a trillionth of a second. These types of lasers allow us to prepare systems in their initial photoexcited states, so we can monitor how long photoexcited populations of electrons and holes persist and try to understand how they lose energy when they relax back to the ground state. In many metal oxide materials, the initial populations begin losing energy within a few picoseconds, a trillionth of a second, and can be fully relaxed by a few microseconds, a millionth of a second. As chemical reactions in solution tend to occur on the millisecond timescale, a thousandth of a second, there can be upwards of 9 orders of magnitude in mismatched kinetics, which represent significant efficiency losses for converting sunlight into chemical fuels. Therefore, using experiments like transient absorption can help us understand how to improve photocarrier lifetimes by reducing or mitigating unwanted reaction pathways. For the sake of time, we'll have to skip over the other techniques, but in summary, they include a unique combination of custom-built and commercial spectroscopies, including photothermal deflection, which measures how materials absorb light, confocal microscopy, photoluminescence spectroscopy, which measures how materials emit light, Fourier transform infrared spectroscopy, and confocal Raman spectroscopy, which informs how chemical bonds in materials vibrate and bend. Many of these can also be performed in operando as materials change under operating conditions in the photoelectrochemical environment. Moving into the microscopy lab, the combination of atomic force microscopy (AFM) and scanning electron microscopy (SEM) enables the nanometer scale imaging of surface topography, morphology, and elemental composition mapping. AFM uses a cantilever with an atomically sharp point to engage the sample surface, and by precisely rastering the tip, the deflection caused by the sample topography is measured. The resulting images offer a unique perspective on the grain structure of semiconductors and catalysts. The tip can also be coated with a conductive metal layer, which allows for the nanometer scale mapping of conductive and photoconductive pathways, which in this image reveals the grain boundaries are more conductive than the bulk crystals, suggesting the grain boundaries play an important role in collecting photogenerated charge. This technique can also be done in photoelectrochemical cells to map processes like photocorrosion, etching, and chemical reactivity of surfaces, as shown in this sequence of images. To stabilize against this type of corrosion behavior, a thin conformal coating of a metal oxide can be used and deposited by atomic layer deposition, or ALD. This highly controlled growth mechanism allows for atomic layer by atomic layer to be constructed on low to high aspect ratio surfaces, allowing for thicknesses of sub-nanometer to tens of nanometer layers to be precisely deposited. Defects caused by dust can create pinholes, thus requiring clean room environments for the most optimal coatings. As an example, under photoelectrochemical conditions, silicon photoanodes become inactive within a few seconds, but with the addition of an atomic layer deposited titanium dioxide layer, 1,000-hour stability has been realized. Having explored the first floor deposition and characterization labs, let's head upstairs to take a look at the wet chemistry synthesis and testing labs. as many materials tend to decompose by dissolving as soluble compounds of their component elements. Sensitive quantification of aqueous concentrations, aided by inductively coupled plasma, mass spectrometry, of those elements can help to understand decomposition rates and mechanisms in hopes of improving it. Other types of surface modifications can be made to semiconductor photoabsorbers through wet chemical approaches to impart unique surface chemical properties, optical properties, and catalytic activity. In these wet chemistry labs, a range of materials and molecules have been created, including lead halide perovskite semiconductors, quantum dots, nanoparticle catalysts, molecular organic frameworks, and inverse opal templated semiconductors. These facilities also enable non-aqueous electrochemical conditions to be explored. Glove boxes provide a clean and inert nitrogen atmosphere for synthesis, testing, and storage of water and oxygen-sensitive compounds. Returning to the first floor for the remainder of the tour, the photoelectrode and dark electrocatalysis testing labs offer sources of pure gas streams of carbon dioxide and carbon monoxide to react with materials such as our copper bismuth oxide semiconductor or metallic copper catalysts, while applying light and an electrical potential to measure current and chemical products produced. As a variety of different gas and liquid phase products can be made from CO2 reduction, sensitive analytical testing methods are required to detect complex mixtures of both. Gas chromatography and high-performance liquid chromatography is used to separate and quantify gas and liquid mixtures respectively. While these measurements typically require multiple minute-long operation of the electrode to accumulate sufficiently high CO2 reduction product concentrations for detection, differential electrochemical mass spectrometry, as shown here, allows for real-time observation of products by pulling them directly out of the water into a high-vacuum analysis chamber through a hydrophobic membrane. Additionally, liquid product identification and quantification is further supported by a 500 MHz NMR, providing chemical information of carbon, hydrogen, and nitrogen bonding environments. And finally, we arrive at the prototyping lab, where the materials being developed, semiconductors, membranes, and catalysts, having been tested piecewise, are brought together into various chassis to evaluate compatibility, efficiency, and stability in long-term indoor and outdoor testing environments. Chassis are being developed around designs which use fully aqueous environments, fully gas-fed architectures, or a mixture of both aqueous and gas-fed. This brings us back to the hydrogen evolving device we saw at the beginning. After seeing how all the components have been synthesized, tested, and studied, we have finally realized a monolithic solar fuels generator. We are really only at the beginning stages of this research and at the outset of the solar age, where the economies of the future and the sustainability of the planet's ecosystems will rely on green energy technologies such as artificial photosynthesis, which will provide a renewable and storable source of green energy while simultaneously reducing atmospheric greenhouse gases. Further information about LiSA, JCAP, LBNL, and my research can be found at the links here.